If your search stack keeps splitting retrieval, filters, and analysis across different systems, LanceDB lets you run full-text, vector, and SQL-driven debugging in one Python workflow. This is the pattern you'll be able to implement by the end, which blends text and vector matching with a filter, and then summarizes with a simple query. I'm Professor Pi, teaching search and IR with simple Python. Search systems get messy fast. You build embeddings in one place. You store text in another. You run analytics in a third. That means more glue code, more sources of bugs, and slower iteration. LanceDB aims to collapse that friction. It gives you vector lookup, full-text retrieval, and SQL analysis inside the same Python flow, so you can prototype and debug quickly. At a high level, hybrid search combines two ideas. First, semantic similarity with embeddings finds things that are close in meaning. Second, full-text scoring finds exact term matches and important keywords. Blend the two and you get stronger, more interpretable results than either alone. Add a simple SQL filter and you can restrict results to a knowledge base or a specific document type. That mix is powerful for FAQ search, support desks, and small knowledge graphs. We will build a tiny end-to-end example you can run locally. You will create a local LanceDB table, insert a few documents with demo embeddings, run vector and BM25 text searches, fuse the scores, apply a filter, and finally run a quick SQL aggregation to inspect how well tags perform. Nothing heavy, just a clear path from data to insight. Now we'll create a tiny LanceDB and run a first vector lookup. This snippet creates a LanceDB database, inserts a tiny document, and runs a first vector search. The variable rows holds a single record with an ID, short text, and a small demo embedding in the vector field. The call to lancedb.connect opens a local store, and createTable writes the rows to a table named docs. The function search takes a query vector and returns the nearest items. Limit narrows the result to one row, and two pandas materializes it for display. The column named _distance is provided by LanceDB and reflects the vector distance metric. The printed top ID and its distance confirm the end-to-end vector lookup works. Next, we'll expand the table and try a BM25 lookup on the text column. This code expands the LanceDB table with two more documents, creates a full-text index on the text column, and executes a BM25 search. The variable more contains two additional records, which are appended using TBL add, so we can search a slightly richer corpus. The function createFTSIndex builds the inverted index that powers text retrieval. The call textSearch issues a query string and returns ranked matches with a score column that reflects BM25 relevance. Limiting to 2 rows keeps the output focused. The printed top ID and BM25 score show the most text-relevant match for the query terms. Now we'll fuse semantic and text signals into a single ranking. This example performs hybrid search by fusing LanceDB vector and full-text scores. The variable vs holds vector results from tbl.search, and ts holds BM25 results from tbl.textSearch for the same information need. The mapping vd converts vector distances into similarities by subtracting from 1, while td keeps text scores as is. The dictionary fused combines both signals per ID using the alpha weight to control the blend. Increasing alpha trusts text more. Decreasing alpha leans on the embedding similarity. The top variable identifies the highest fused score. The printed hybrid ID and fused score demonstrate how combining signals improves ranking robustness. Next, we'll show how to restrict semantic search to a specific content source. This snippet narrows LanceDB vector search to knowledge-based content using a structured filter. The call to search retrieves candidates for the same query vector, and where applies a SQL-style predicate on the source field, so only rows from KB remain. The limit keeps 2 results to ensure a stable top choice, and 2 pandas converts the hits for inspection. This approach is useful when blending semantic search with business constraints like document type or visibility. If the filter is made stricter, you may trade recall for higher precision. The printed filtered ID and distance confirm the constraint changed the top match set. Finally, we'll pull the retrieval hits into DuckDB and run a quick aggregate. This code runs a quick SQL aggregation over LanceDB's search results using DuckDB. The variable TS captures BM25 hits from tbl.textsearch as a small data frame. A DuckDB in-process connection is created, and register exposes the hits as a SQL table named hits. The query computes average text relevance per tag, orders by that average, and selects the best performing tag. You can extend this to slice by source, compute recall proxies, or compare different queries uniformly. Reducing the limit tightens latency. Increasing it gives more stable aggregates. The printed top tag and its average score give a compact, actionable summary of retrieval quality. If you map this toy example to a real project, the same steps hold. Use your real embeddings instead of demo vectors. Use your tag or source fields to enforce business rules. The SQL aggregation becomes a monitoring query you run periodically to detect drift or regressions. Recap. What it is: a single Python workflow that runs vector search, BM25, hybrid fusion, filters, and SQL summary in one place. When to use it? When you want fast iteration on retrieval logic and tight integration of semantic and lexical signals. One caveat: hybrid scoring needs tuning. A bad alpha can hide useful results. Next step: tune the alpha blending weight and measure how rankings change on a held-out set, or scale the vector index and rerun the same SQL summaries for stability. That single change will teach you how much text versus semantics matters in your corpus. If short, practical IR helps, subscribe and watch the IR videos.